So, good morning, guys. I hope you're having an okay week. We're going to go ahead and continue our discussion on heat exchangers, picking up a little bit from where we left off on Monday, and hopefully talking about the design equation in greater detail. So let me make sure I have the right color. So we're talking about heat exchangers. From last time. I stated for a given system, when we're exchanging heat or thermal energy, between two fluids in a heat exchanger, we have to consider the change in internal energy via thermodynamics that can be determined as MCP delta T. So I can consider the heat transfer out of the hot fluid as the mass flow rate of the hot fluid, the heat capacity of the hot fluid times the temperature of the hot fluid in minus the temperature of the hot fluid out. I can also state that heat transfer is also coming into the cold fluid. So MCP, MC, CPC, T cold out minus T cold in, where QH equals QC equals Q. And we also stated that when looking at heat transfer via a heat exchanger, we can rely on our design equation for heat exchanger that says Q is equal to U times A times F times delta T log mean. Where U is our overall heat transfer coefficient. A sub S is our heat transfer area or surface area. F is, I'll call it a flow corrective factor. We'll talk about that here in a little while. And delta T log mean is our log mean temperature driving force. So today I want to kind of break down some of the more undefined terms within the design equation, starting with U, our overall heat transfer coefficient. If I look at basic flow through a heat exchanger, I'm going to have some fluid on the outside and some fluid on the inside. So I'm drawing just kind of cold fluid on the inside, hot fluid surrounding the cold fluid, with the heat transfer coming from the outside in. Now with this, the heat transfer can be described as in terms of several factors. So I'm going to say, looking, it's a simple double pipe. I can consider and calculate the heat transfer associated with the outside fluid, the heat transfer associated with the inside fluid, and any thermal resistance that I see associated with the pipe itself. And the total heat transfer coefficient, or the overall heat transfer coefficient, ends up being a function of each of these three terms, such that I can calculate my overall heat transfer coefficient U as a 1 times HO A sub O plus ln dO over dI divided by 2 pi KL plus 1 over HI A sub I to the negative 1. Now, what do these terms look like?
The R values.
Yeah, they look like thermal resistance values, right? And so I can also state that U is simply just the inverse of a total thermal resistance if I consider these resistances existing in series, right? I have our convection, R of a cylinder, and then R of a convection again, right? This is on the outside, this is on the inside, right? So I add those up, I get a total thermal resistance, I take the inverse, and I'm left with a heat transfer coefficient. Now, oftentimes, we can approximate our U value using a simplified equation, or actually a simplified expression. And I do this by assuming a couple things. First, if the pipe thickness is small, I typically say A is about the same area as A sub I. And if my pipe is made out of a metal or something with a high thermal conductivity, I can also assume that that thermal resistance by the pipe wall is negligible. And if I do that, I get into a simplified expression for U, 1 over HI plus 1 over HO to the inverse. And this is often used for heat exchanger design calculations. And so you'll probably, for those of you in design 1, you've probably seen this form when determining your overall heat transfer coefficients. And so it's a little different from what we see, right? Because if we're using a reasonable metal with a good thermal conductivity, comparing that resistance value to the convection resistance, we find that the convection resistance typically dominates. And at the same time, it's very rare you're going to have an extremely thick wall in your the piping in your heat exchanger, and so a lot of times you don't have to do a corrective value for your areas. However, for exchangers in operation, we often consider the effects of fouling on heat transfer performance. So what do you think I mean by fouling when it comes to this heat exchanger?
Like that could be like tube plugging.
Stuff like that.
I heard two people. I heard tube plugging. What was the other thing I heard?
Like build up around your pipe walls and stuff.
Yeah. So when I consider fouling, I'm talking about the accumulation of deposits on the surface of the pipes within my heat exchanger. right? So if I were to draw this out again, my little simplified heat exchanger, I have one fluid here, and now I'm changing it up. How dare you? In addition to having the resistances I've identified, if I start to see the accumulation of deposits on the tube surface, and it can happen both on the outside and I don't know, what's that one that'll be really weird to stand out, and on the inside. I can have fouling on either side of my tube. But you can see how that's going to influence my ability to have heat transfer in my heat exchanger. Right? And so what it ends up with is I have another heat transfer resistance that I have to consider. And so when I'm looking at determining the overall heat transfer coefficient for an exchanger in operation, the U, I can write this full expression that says U is equal to 1 over HI A sub I plus R F sub I over A sub I plus ln of dO over dI over 2 pi KL plus R F sub O over A sub O plus 1 over HO AO to the negative 1. And so I have my convection resistance here, my material conduction resistance through the pipe, or cylinder, and then I have a fouling resistance on the inside and on the outside of my pipe. And so I end up with 5 thermal resistances for my heat transfer. And I'm considering essentially a heat exchanger that's been in operation for a while, because the longer a heat exchanger operates, the more likely it is you're going to see fouling on those pipe surfaces. So with this kind of in mind is, what do we think or what do we expect to happen to our heat exchanger's performance as fouling accumulates?
It will decrease the rate at which heat is transferred.
All right, so we expect Q to decrease, right? So Q will decrease. Here, I'll use not red. I like using red for questions. I agree, Q will decrease. U will also decrease, right? Because if I'm adding that thermal resistance, adding those new terms, the inverse of that will be a smaller value. And what do we expect to see to happen to our temperatures leaving our heat exchanger?
They'll be more extreme, meaning instead of being closer to the same temperature, they'll be more divergent from that temperature.
There won't be much change in the temperature throughout the heat exchanger.
There'll be a lesser temperature change for the fluids, right? Based on the design equation, which we have up here, if this Q is smaller, then the delta T is on both the hot side and the fluid, and the cold side of the fluid will be smaller, which means the hot side isn't going to cool as much and the cold side isn't going to be heated as much. And so you'll start to see deviations from any desired set points or operating points in your fluid temperatures leaving that heat exchanger. Which means if you're using a utility on one side, you're going to have to start burning more utility or clean your heat exchanger. Granted, that's a design thing we'll get to in design 2, but it's always good things to keep in mind. So let's take a look at an example and see what we can do. We have a double pipe heat exchanger constructed of stainless steel with a thermal conductivity of 15 watts per meter Kelvin. And the inner diameter is 1.5 centimeters. The outer diameter is 3.2 centimeters. If the heat transfer coefficients in the heat exchanger are given as 800 watts per meter squared Kelvin and 1200 watts per meter squared Kelvin, determine the total thermal resistance and the overall heat transfer coefficient for this heat exchanger, provided we have the two values for fouling provided, 0.0004 meter squared Kelvin per watt and 0.0001 meter squared Kelvin per watt. So go ahead and write this down. I want to shoot you guys in breakout rooms for about 5 minutes to see how well you guys can do. Break up class a little bit. If it helps, go ahead and take a picture of this so that you have all the information if you don't want to take the time to write it all down before you start working together. I will say for this, go ahead and assume a basis for your area. And you can just assume, area outside and area inside are reasonably the same, and just assume a basis of 1 square meter of area. So any last minute questions before I shoot you guys into breakouts? All right, good luck. Let me know how it goes.
Dr. Lopez,
Yes, sir.
I don't know if you saw my email this morning. I had to go home for a funeral.
Okay, I'm so sorry to hear that.
Oh, thank you. But my hometown is in the path of Hurricane Zeta, so I might not have power tomorrow.
No problem. I understand. Just keep me informed, and if you need an accommodation or anything, just like I said, try to shoot me a email if and when you can, and I'd be more than happy to accommodate
Yes,
you.
sir. I'll let you know as soon as possible if we
No
lose.
problem. You got other things to focus on. So like I always tell students, life is more important than school. So focus on what you need to. And I'm sorry
All right, thank you so
to hear
much.
about that. No problem.
Let me hop in this breakout room.
How's it going, guys?
How's it going, Dr. Lopez?
Good. You guys have any questions, or you kind of have a good idea of what you need to be doing?
So
Should
you
we
want us?
assume, oh, sorry, go ahead.
Go ahead, Miranda. You got it.
Okay. Should we assume the length for the middle term to be 1 as well as the area?
Yeah, you can. Yep.
Okay.
When in doubt, assume it out.
Does 66 sound about right?
For you,
Yeah.
I ended up with 94.
Oh, okay.
Double check your units because your units can be a little weird here.
Okay. I'll do that.
Yeah, because you want all your resistance terms in that expression to be either in meter squared Kelvin per watt or Kelvin per watt.
Okay.
So because this is a double pipe, that doesn't actually change how we calculate our U?
Nope.
Okay. Does that mean so U's going to stay the same within a heat exchanger then?
Yeah. Well,
Okay.
we'll talk about what really happens when we look at heat exchangers a lot of times is that's where that F value comes in.
Yeah. Okay. Well, that's not. Yeah. Okay. That's what you mean for the phase change and all that. Cool.
Okay.
Okay, that's not good.
All right, I'll let you work. Finish it up.
I've done something wrong, but
What did you get?
I got something like it was like like 9. I think I messed up my units somewhere or something. I know it's not 9.
Yeah, I struggle with the units on the LN term because you get watts per meter Kelvin, and I guess if you multiplied by the length, you'd have meters. Well, your meter would cancel, I guess, and you'd get watts per Kelvin. But right now we don't have a length.
You can assume a length of 1.
Okay.
Dr. Lopez, my answer of 9 was not correct, was it?
You're off by an order of magnitude. It should be like 90 something.
Okay.
For you,
Yeah.
like 94.1.
Yep.
Okay.
So you can explain to
So
your
we can
group.
assume a length of 1. Is that right, Dr. Lopez?
Yes, you can.
Okay, cool. Thank you.
No problem. Hello, hello. How's it going, everyone?
It's going all right.
Are you guys able to arrive at an answer? Are you having trouble? Questions?
We were mainly just trying to figure it out on our own, but I ended up getting the value for the thermal resistance as 0.009 kelvins per watt per 1 meter length. That's
about what I have.
And I got the value for the overall heat transfer coefficient U to be around 11.625, assuming it's a 1 meter length.
I surprisingly ended up with that's low. I got around 94.
All right, maybe I just put the math here in wrong, I guess. I'll take a look at it again.
No problem. Give you all a few more minutes to work up.
.96 e to the -3rd. I guess it's in Kelvin per watt meter.
Look at you guys. You guys are so organized. You got screen share going.
Mine was definitely not close to that. I did something very wrong.
You could have done something very right.
Yeah, I think we're trying to get the overall U.
What did y'all get for overall?
Hmm.
I got 0.052.
Welcome back. All right. So I was able to get into a few rooms and see how you all are doing. I appreciate you guys all working hard on the problem. Let's see if we can talk and work it out as a class. So I know there was probably at least a couple groups that were able to get to the solution, but for those of you that were still wrestling it out, I'll give you guys a quick rundown of what I have in this example. So for this problem, we're looking at finding both the total resistance and the overall heat transfer coefficient. Since the total resistance is simply 1 over U, I can write R total as essentially the same equation as U, just without the inverse at the end. Or it'll look something like this. And I'm going to assume AO is equal to AI, which is 1 square meter, and the length. I had a couple people ask if you could just assume it's 1 meter too. So that means our total resistance should be about 1 over 800 watts per meter squared Kelvin times the area, which is 1 meter squared, plus the fouling value on the inside, which was 0.004 meter squared Kelvin per watt, divided by 1 meter squared, plus the ln of 3.2 divided by 1.5 divided by 2 pi 15 watts per meter Kelvin times 1 meter, plus the resistance or the fouling resistance on the outside, which is 0.001 meter squared Kelvin per watt divided by 1 meter squared, plus 1 divided by 1200 watts per meter squared Kelvin times 1 meter squared.
You missed a 0 in your RI and RF.
Oh, thank you.
Okay.
That's it. 3 zeros, you are correct. Thank you for that. 0004 and 0001. So it's a little bit of a mouthful. But if you do this calculation for R total, you should get a value of approximately 0.0106 or 011 Kelvin per watt, which means if you take the inverse of that, you get U is about 94 watts per Kelvin per meter squared, right? Because that's our basis.
Would your length not be like a function of your surface area that you assume?
It would, but for the intents and purposes of this problem, I really didn't give you, well, I guess I did technically give you a diameter. So you could technically back out the length. Because if the surface area basis was, see, then that gets tricky because then my assumption of AO and AI fall kind of breaks down a little bit. So technically, yes, you could back out a different length based off those areas. But I wasn't really focusing on that in the problem. I was just wanting you guys to get practice using the expression.
I think there might be an error on the slides for this equation. I think it's slide 4. It's the same equation you wrote, but it has U instead of R.
Oh, thanks for that. Yeah, it's missing the inverse. I see that error now. All right, I'll make that correction in Blackboard after class. So any other questions on this example?
I was going to ask that in the slide before this, it said U was equal to the equation used for R.
Yes.
Is that supposed to be right in that the solving for that it's R equals that equation instead of U, or is it U still equal to that equation?
Yeah, that was what was just brought up, that the equation was missing an inverse.
Okay. Yeah, that would be it.
What I presented in the lecture is correct. I'll update the slides after class, and I'll send a follow-up email as well. All right, so the next thing I want to talk about in our design expression is our correction factor, F. And the purpose of F is to correct for non-idealities of flow direction within a heat exchanger. Because if I look at a heat exchanger, and I wish I would have still brought that up. I might be able to bring it up really quickly. We had talked about how ideally we would like to see countercurrent flow as it provides the best and more stable driving force throughout our exchanger. However, the fluid within a heat exchanger flows in a more irregular pattern. And let's see if I can pull this up so you guys can see it. So if I share, see, can you guys see this video?
Yeah, you can see it.
Yes.
Okay. So in this video, it's actually a work in progress for some hands-on modules for this course. You see what's known as this double pipe heat exchanger. And the heat transfer fluid is, the hot fluid is designated by this red fluid, and the cold fluid is designated by the blue fluid. The hot fluid enters the heat exchanger on the top, and it moves on the interior. So it's what we call the tube side of the heat exchanger before it essentially leaves out of the bottom of this heat exchanger. And to counter this, the blue fluid enters the bottom on the shell side or outside of those tubes, and it moves up through the heat exchanger where it leaves out of the top of the exchanger. So when I hit play, it's a short video, you can see how these fluids are flowing through this heat exchanger. However, while for the majority of flow, we can say that these fluids are flowing in a countercurrent fashion, right? Because hot fluid's going to be moving top to bottom, from right to left and left to right, and the cold fluid's moving from bottom up, always opposing the direction of flow as compared to the hot fluid. However, there are sections where the cold fluid's moving up as well as the hot fluid's moving down, outside and away from those fluids. And so we don't have perfect contact, and we don't have essentially perfect countercurrent flow. And the way we can correct for that is by use of our F factor. And so we can basically institute this correction factor, which allows us to use or assume a countercurrent flow path for our delta T our log mean temperature gradient, and then correct that temperature gradient with this F value. And so in general, F goes from 0 to 1, 9 times out of 10 if I'm honest. It typically goes from 0.5 to 1, where F equals to 1 means that you have essentially idealized countercurrent flow within your exchanger. For most exchangers, we can get pretty close to an F value of 1. And the way we calculate F, if you want to, is through an expression, equation 15.1 in your text on page. Let me see, where's the page for this one? .446. And so we can calculate F as a quantity z squared plus 1 to the 1/2 power times the natural log of 1 minus eta h minus over 1 minus z times eta h divided by z minus 1 times the natural log of 2 minus eta sub h times z plus 1 minus z squared plus 1 to the 1/2 power divided by 2 minus eta h z plus 1 plus z squared plus 1 to the 1/2 power, where z is equal to the temperature of the hot side in minus the temperature of the hot side out divided by the temperature of the cold side out minus the temperature of the cold side in. And this eta sub h value is equal to temperature of the cold side out minus temperature of the cold side in over temperature of the hot side in minus temperature of the cold side in. And so by looking at the relative temperature differences at the entrance and exit of a heat exchanger, we can calculate the corrective factor for our driving forces. Now, this is all well and good, but to be honest, 9 times out of 10, we typically don't want to calculate it this way. Also, one other thing, Z can also be calculated as a ratio of the heat capacities because of the nature of how the heat transfer can be calculated. So depending on what's provided in the problem. A much easier way to calculate this information is, once again, through use of a helpful chart, where instead of having to do that giant F equation, we can simply calculate our Z value and our eta value and find the intersection between Z and eta, and then go to the y-axis to find our F. Now, one thing to keep in mind is these correction factor figures are typically for a particular set or class of exchangers. For example, the figure that I'm showing here on this lecture slide 12 is for a 1-2 shell and tube heat exchanger, meaning it's a heat exchanger that has 1 shell pass and 2 tube passes. And so you can imagine the more complicated the heat exchanger, the differences will arise in your corrective factors. So it's important when looking at determining your F value to use the appropriate figure for the heat exchanger that you have.
What page is that on?
This figure is on 447. There's also an example of a 2-4 figure for a 2 shell pass, 4 tube pass shell and tube heat exchanger on 448. Any questions on that? Like I said, 9 times out of 10, you really don't want to have to do all this calculations just because it can be lengthy. And so it's much easier to rely on the use of the figures. It'll get you close enough. One thing I will say is be careful when doing some of these calculations, because you'll see, for example, if you calculate an eta value of 0.5 and a z value of 3, that's going to represent an exchanger that can't really exist. And so if you run into an issue where the eta and z's don't match up, that means you have some sort of error in your calculations or in your exchanger design. Because in order to get something that makes sense, you have to make sure that those values can intersect. Kind of like when we talked about in our TXY diagrams where you don't want to make the thermo break in your system. Any questions on that? If not, we can wrap up today looking at a simple expression. So in a 1-2 heat exchanger, the values of the temperatures on the inlet and outlet were taken. The question asks, what is the corrected log mean temperature gradient? So let's see if this one makes sense and if we can get a corrected log mean temperature difference. So what is delta T log mean? And I typically designate it with a bar, which is really just the delta T log mean times F. So I know T hot in is 240 degrees. T hot out equals 120 degrees. T C in is 65 degrees. And TC out is 100 degrees C. So I'm going to assume countercurrent flow for determining delta T log mean. And so that means my hot fluid in is going to interact with my cold fluid out, and my cold fluid in is going to interact with my hot fluid out. Or delta T1 is going to be 240 degrees C minus 100 degrees C, which equals 140 degrees C. My delta T2 is going to be 120 degrees C minus 65 degrees C, which is 55 degrees C, which means my delta T log mean is going to be 140 minus 55 divided by the natural log of 140 over 55 degrees. So if I do this calculation, let's see what I get. Approximately 90.9 degrees C for my driving force. But I have to do a correction factor, so I need to find my Z and my eta. So from here, Z is hot in minus hot out over cold out minus cold in, or 240 minus 120 divided by 100 over 65. Double check that. So I get a value of 3.5. And my eta is CO minus CI over HI minus CI, or 100 minus 65 over 240 minus, what's it called, N, 65. Point 2. So taking a look at this one, if I have a Z of 3.5 and an eta of 0.2, I say, okay, 3.5, eta is 0.2, I get an F value of approximately probably around 0.9. So this is my eta, 0.2. I follow that all the way up where it intersects with a Z curve of about 3.5, which I would say probably halfway between 3 and 4.
Still looking at your notes, not the PowerPoint.
Thanks for that. Okay, now that you can see what I can see, I see it here. So that's where I would find that intersection. So my F is about 0.9, which means, which implies delta T log mean bar is equal to 90.9 degrees times 0.9. Right, so it's a corrective factor saying your driving force is lower than your initial calculations will tell you. So your actual log mean driving force is about 82 degrees. Any questions on that? So like I said, I know it looks a little complicated, especially the full F equation. That's why we have these graphs that, for the most part, are helpful. All right, if not, that's all I have for you guys today. Don't forget, your midterm is tomorrow evening from 6 to 9. I will be hosting a review session this evening from 5 to 7. I will send out an email either later this morning or early this afternoon with the Zoom link to join that review session. So please come with questions, and I'd be more than happy to answer them, work through things, clarify things. I want to make sure you guys are as confident going into this midterm as possible. If not, take care, guys. Have a great rest of your day, and I hope to see you this evening.
Thank you.
All right, take care, guys.
Thank you.